Hello and welcome. In today's video, we're going to be going over topic 4.5, graphing. So, I just want to take a step back for a moment. Throughout your algebra days, you may have graphed a function. Now, the cool thing about calculus is it gives us more tools for graphing. For example, it may be difficult for us to find what the maximum of a cubic is, or rather a quintic, or a minimum of a fifth degree polynomial, as well as things like exponentials. And calculus gives us the tools that we need to really broaden that out and find these areas of issue. Really, it helps us fill out the graph. So what I have here for us today is we're going to be going through how to graph things using calculus. So, of course, we have to start out by knowing the basics. Alright? And I'm actually going to add in one more thing here, and the end behavior. Alright. So, we want to find the following if f of x is equal to x to the fourth minus 4x. So what we have to do is we have to start out by taking the derivative. So we get f prime of x is equal to 4x cubed minus 4. Alright. Now, what does this actually tell us? Well, since we're looking at f prime, this is going to give us information about where f is increasing or decreasing. So what we want to do is we want to set this to 0. And then we are going to solve for solve for x. So we get an answer of x is equal to 1. Of course, there's two imaginary roots to that as well. However, we don't have to worry about those. Now we're going to come back to the trusty number line that I've been encouraging you to use. And you may notice my system looks a small bit differently today. And that's just because of I got a new app to do this on. So we know our 0 is 1 for f prime. So if we plug in a value to the left, well, let's say I plug in a value of 0. This is going to clearly be negative, so f is decreasing. However, if I plug in a value greater than 1, let's say 2, 2 cubed is 8, 4 times by 8 is 32, minus 4, that is positive. So f will be increasing. So our answer to A is f is increasing from 1 to infinity. And sorry, you should, or don't include the infinity, but do include the 1. And then f is decreasing from negative infinity to including 1, which is kind of interesting that a function can be increasing and decreasing at a point. So now we want to find where f is concave down or concave up. Well, we use the second derivative to tell concavity because it's the rate of change of the derivative of f. Alright, so we will have the derivative of x cubed is 3x squared, so it will become 12x squared minus 0. Set that equal to 0. Set that expression equal to 0. Alright, so 0 is equal to 12x squared. So x squared must be equal to 0. So x must be equal to plus or minus 0, which is really just 0. Alright. So now what we have to do is we're going to graph x squared here. F double prime. Not graph it. I am I apologize, but we're going to say 0. If we plug in a value to the left of 0, we are going to clearly see that because we're squaring it, it's going to be positive, even if we plug in like negative infinity. And to the right, it's also going to be positive, so it's also going to be positive infinity. So what we're going to get is f is concave up for negative infinity to 0, or 0 to infinity. And you may notice I did not include the endpoint there. And that's just because it's concavity. We don't include endpoints in concavity. Now for finding the local extrema of f, you may recall that f will have a extrema or a possible extrema at where the derivative is 0, or where it's undefined. Well, because this is a polynomial, it's not going to be ever undefined, but we have found it's 0. And its 0 is at x is equal to 1. Well, because f goes from from decreasing to increasing at x is equal to 1, x is equal to 1 will be a minimum. So now we have to find the x-coordinate. So there's a min at 1 comma. So now we just have to find the y-coordinate, sorry. So we plug in 1 into our original function. 1 to the 4th is just 1, minus 4, so negative 3. All right. Now we want to find the absolute extrema for f. Well, because we have only 1 point extrema, and we know f is decreasing everywhere to the left of this point and increasing everywhere to the right of this point, we know that the absolute minimum, so the absolute min, must be y is equal to negative 3. Alrighty. So now we want to find all the points of inflection of f. Well, if we want to know the points of inflection, we have to know where the derivative, the second derivative of f, is 0 or undefined, which we already did. How useful is this number line test? Alright. Well, because this 0 does not change sign, there is no POIs, or points of inflection. And finally, we want to know the end behavior. Well, if we take the limit as x approaches infinity of x to the 4th minus 4x, that is going to approach infinity. Because even though there's this minus 4x, this x to the 4th is going to be growing larger at a faster rate. It has a higher magnitude. Now, if you're approaching negative infinity, again, this x to the 4th is going to be a higher magnitude, and since it's an even power, this is going to approach positive infinity. All right. So, what are we actually looking for when we're graphing? Or really, what are these guidelines? So, following a checklist intended to guide for sketching a curve f of x by hand kind of makes it a bit easier for sketching a graph. So, of course, it's often useful to start by knowing the domain of your function. For example, it's useful to know that a function's domain is only defined from 0 to 3. Or perhaps it has some discontinuities in it, such as with like a tangent or a cotangent or any of the reciprocal trig functions. Alright. So the next thing we want to look for is the intercepts. We want to know all the intercepts of a graph. For example, the y-intercept and the x-intercept. So we can easily tell where x or the f of x is 0 or very easy values of f to evaluate. However, you can omit this step if the equation is difficult to solve. The next thing we want to look at is symmetry, because sometimes we have functions that are symmetrical, and that makes them very easy to graph if you have like a left side and a right side. If the graph is symmetric, then all you have to do is flip it over the y-axis, or sorry, if it's even, all you have to do is flip it over the x-axis or y-axis. And if it's odd, all you have to do is rotate it about 180 degrees about the origin. All right. Well, what about asymptotes? Well, we want to be looking for all of the asymptotes, which includes slant asymptotes, horizontal asymptotes, and then vertical asymptotes. Which a slant asymptote is just whenever the limit as x approaches infinity, it starts looking like a line. And this happens when the degree of the numerator is 1 higher than the degree of the denominator. Horizontal asymptotes happen whenever you're approaching a certain number as you go to infinity, and vertical asymptotes happen whenever you're approaching a certain number and you go to positive or negative infinity. All right. So then we need to also find the intervals where f is increasing or decreasing. This allows us to help sketch out a smooth curve. And then we want to use concavity and points of inflection also in said graph. And sorry, I missed one. And then we also want the local maximum and minimum values, which we've already talked about in earlier videos. Then we just have to sketch the graph of f. So I want to start out here by sketching the curve y is equal to 2x squared. All right, so how are we going to do this? Well, I say that we start out with the domain. We want to know where the domain of this function is going to be undefined. So the domain, that is not a pretty color. There we go. Domain is going to be x, given that x squared minus 1 cannot be equal to 0. So we know that, so x given x squared, x cannot be equal to plus or minus 1. All right. And that should give us all of our values for undefined. So we know that the domain is going to be from negative infinity to negative 1, or negative 1 to 1, or 1 to infinity. All right. So now we want to find the symmetry, or see if there's symmetry in this. So in this case, if we plug in negative x to f of x, so f of negative x, and actually the way that we're going to do this is we're just going to set this up as such, is equal to 2 times by negative x squared divided by negative x squared minus 1. Well, we can clearly see that the value of the numerator is still going to just be x squared, and the denominator is going to be x squared minus 1. So they are equivalent. So this function is even. Okay. So now what we want to do is that we want to find the asymptotes. So if we take the limit as x approaches plus or minus infinity, so we take the limit as x approaches plus or minus infinity of 2x squared over x squared minus 1, we will clearly see that the minus 1 is kind of going to be insignificant. So this function is going to look more and more like the limit as x approaches plus or minus infinity of 2x squared over x squared. Well, the x squareds will cancel, and this is just going to leave us an answer of 2. So the limit as x approaches plus or minus infinity will be 2. All right. Well, now we also need to find the asymptotes, and we have several good candidates for asymptotes. So the limit as x approaches -1 from the left of, we're going to call this function y. Well, as we approach it from the left, we're going to be plugging in values just barely bigger than negative, or barely smaller than -1. Think like negative point or -1.001. Well, this is going to get closer and closer to 0. And because this denominator is going to 0 and this numerator is still equal to something, this is going to go to infinity. Negative infinity. Then, looking at the limit as x approaches -1 from the right, we see that y is going to approach infinity. Alright. Well, now as the limit as x approaches infinity, not -1, not infinity, so we want to approach 1 from the left of y, that will approach infinity, and then the limit as x approaches 1 from the right of y is going to be -infinity. That was like the strangest negative infinity I could have ever done. Alright. Then after that, now that we've found all the asymptotes, or at least we know that there's going to be vertical asymptotes at x is equal to -1 and x is equal to 1. Maybe clear up a small bit of this work here so we have more space. Make sure to keep all of our important information that we have so far. Alright. Then we have to find where it's increasing or decreasing. So this requires us to take the derivative. So y prime in this case is going to be the derivative of the top, which is 4x, times by the bottom, which is x squared minus 1. Alright. Minus 2x squared times by the derivative of the bottom, which is 2x, all over x squared minus 1 squared. So what we're going to do is we're going to expand this function out. So we get 4x cubed minus 4x minus 4x cubed all over x squared minus 1 squared. Well, the two 4x cubes cancel, leaving us with just -4x divided by x squared minus 1. Now, what we have to do is we have to solve this for 0. Or for 0 and where it's undefined. So, we get -4x is equal to 0, and x squared minus 1 is equal to 0, as those are possible points where it will be undefined. Well, we get x is equal to 0 for the solution to the left equation, and we get x is equal to plus or minus 1 for the solution on the right. Well, we are now going to use our very handy number line, going from 0, -1 to 1. And we're just going to, and I suppose I should maybe make that a bit wider. Now that we have the number line sketched, we're going to plug in a value. Let's say we plug in negative infinity for estimating this interval over here. Well, the numerator is going to become positive. So we get positive, and then the denominator, since we have this x squared, is also going to be positive, so it's increasing. Alright. Then for this -1 to 0, what we're going to see is that we're going to plug in like a value, let's say -1/2. The numerator is going to be positive still, but the new denominator is now going to be negative, since we're going to be like squaring 1/2, which becomes 1/4, and that's going to be -1. Now what you'll see is, interestingly enough, whenever because we know that this is an even function, this, sorry, I realize I've made a small bit of a mistake here, but this denominator is always going to be positive because we're squaring it. So we get this plus, or we get this interval where x is going to be increasing. And then, because this is an even function, whenever we check these other two intervals, we're going to see that they're going to be negative. And if you don't believe me, plug in 1/2. Well, the numerator is now going to be negative. However, the denominator is always positive, so that must be negative, or decreasing. And then from 1 to infinity, plug in no matter how big of a number you choose, that is going to be negative. So it's going to be decreasing in the numerator. So what we get here is f is increasing from -infinity to 0. And we do include the 0. Actually, we can't include, give me one moment. I do have to change this up just a small bit. Because -1 is undefined, f is increasing from -infinity to -1. And we can't include that. And then from -1 to 0. However, we can include the 0. F is decreasing from 0 to 1, including 0, not including 1, and then from 1 to infinity. Alright. Now let's look at relative mins and maxes. So, we now have, so whenever looking at mins and maxes, we just want to know where the sign swaps, or, yeah. So, we want to be looking where the f prime sign swaps. So we can see here at 0, f prime, or from, at x is equal to -1, because the sign does not swap, this is a shelf point. So it just goes from increasing to increasing. And it doesn't really have a maximum or a minimum there. At x is equal to 0, there will be a maximum. So max at -1. And then we now have to plug in the value here into our original function. So we get -1 squared is 1. So we get 2 divided by -1 squared. Or sorry, not -1, sorry, 0 is the point that I wanted. So from 0 to, or not from 0, but from the point 0 And then whenever we plug in 0, we get 0 in the numerator, but in the denominator, we get -1. So it's going to be 0, 0. All right, so now that we've found the one critical point, and then this one is not going to be a critical point because it goes from negative to negative as the sign doesn't change. So now we got to clean up the board. Alrighty, now for the concavity, we have to take the second derivative. So we will get y prime, or y double prime is equal to the derivative of the top, which is -4, times by the bottom, which is just x squared minus 1 squared, minus, which is going to become a 4x, plus 4x, sorry, times by the derivative of the bottom, which is going to be 2 times by x squared minus 1, apologies, times by the derivative of the inside, which is 2x. All of this is over x squared minus 1 to the 4th now. Well, we are going to cancel this 4th and make it into the 3rd and cancel the 2 grouped things in the numerator. So we're going to get y double prime is going to be -4 x squared plus 4 plus 4x, alrighty, plus, well, 2 times by 4x, that's going to give us 8x, times by 2x squared, that's going to give us plus 16x squared. Accidentally accounted for this 4x twice. All over x squared minus 1. So now we're going to get y squared, or y double prime, not y squared, I'm kind of tired here, is equal to 12x squared plus 4 divided by x squared minus 1 cubed. Well, we're going to use the same number line tactic that we have been using. And we need to find the zeros. So we get 12x squared plus 4 is equal to 0. Well, that means that 12x squared must be equal to -4. So x squared must be -4 over 12, which will simplify to -1/3. However, taking the square root of that is going to give us an imaginary number. So we don't have to worry about the numerator in this case for being a point of inflection. However, we do have to worry about the denominator. So we get x squared minus 1 cubed is equal to 0. Well, we have the point right here where it might change. However, or rather, taking the cube root of both sides, we get 0 is equal to x squared minus 1. So x plus 1 and x minus 1 are going to be our possible solutions. So x is equal to -1 or x is equal to 1. So now what we're going to do is we're going to plug in some values here. So no matter what, the numerator is going to be positive. So we're just going to write a big old fat plus. However, what we want to look at here is the denominator. So if we plug in a value of, let's say, 0, well, we're going to get 0 squared minus 1, which is going to be -1. Cubing that is going to give us -1 cubed. So the denominator is going to be negative. So it's going to be concave down from -1 to 1. All right. Well, let's say if I plug in a value like -100. Well, the numerator is still going to be positive. And in this case, the numerator is also going to be positive. So it's going to be concave up. Finally, if I plug in a really big number like 100, the numerator is always positive, but the denominator is now going to be like 10,000 minus 1 cubed. That's going to be a very big positive number. So it's going to, again, be positive over positive. So the function is going to be concave up from 1 to infinity. So now that we have all of let's real quickly just mark out our points of inflection here. So we're going to say our POI are going to be negative x is equal to -1 and 1, which we know aren't going to have points because those are outside of the domain. All right. Let's real quickly just get a small bit of stuff cleared off so we can have space. Actually, I only want to get rid of that. All right, there we go. And there we go. There we go. And delete that from existence. So, now we have the concavities and points of inflection. We have everything we need to graph. So we want to choose this so we get all of the values that we want inside of our domain here. So we start out and we want to go, let's say, 3 out from where our important values are. This is not necessary for everyone. This is just what I'm doing. Then what I want to do is mark out any asymptotes, vertical or horizontal, which there is one I forgot to mention, which was the limit as we went out to infinity here was going to be equal to 2. So we're going to have a horizontal asymptote at y is equal to 2. We're going to have vertical asymptotes as labeled at -1 here and 1. All right. Now what do we do? Well, we need to plot a point. Well, we know what the relative maximum is. It's 0, 0 here. So we're going to plot that point. And now let's look around this point to see what's going on. Well, we know f is increasing from -infinity to -1. However, we know it's also approaching this asymptote. So let's graph it. Well, we know that there's a vertical asymptote here. And as we approach -1 from the left, we found out that it's going to approach infinity. All right. Then, as we approach -1 from the right, it's going to approach -infinity. All right. Then, as it approaches 1 from the left, it's going to approach -infinity. And finally, as it approaches 1 from the right, it's going to approach +infinity. So we're going to kind of get a graph that looks like this. Well, we have another bit of important information that we're supposed to do. What is the concavity of the graph? Well, we can clearly see that this graph is concave up, and it looks like I accidentally forgot to write down where the concavity was. Give me one moment and I'll write. Now that we have the concavities, we can clearly see this function is concave up already from -infinity to -1, and it's concave down from -1 to 1, and concave up from 1 to infinity. And we have our relative max. So in this case, we have everything we need to graph. And we have graphed, as this is our function y. Well, this is all I have for you today. I'm going to give you 2 more example problems that you can work on. I'm not going to do them in this video because it'll be too long. But for one, we have y is equal to cosine of x divided by 1 plus sine of x. And the other is the natural log of 4 minus x squared. Well, that's all I have for you. In the next video, we are going to be going over optimization. Well, I hope you have a wonderful rest of your day and enjoy. Bye bye.